Okay, guys, let's get started with 15F, our last exercise for our last semester of Year 11 Maths. So we're doing optimization, right? And we've got a really good way to explain it for you. Here is a glass of water, and the optimist will say to you, the glass is half full. And the pessimist will say the glass is half empty. And what does the engineer say? The glass is twice the size it needs to be. All right, so engineering is all about optimization, right? And so optimization means finding the most economical solution, the one that's going to save us the most, be it money or man hours or labor or whatever it is. We're trying to save the most, we're trying to find the best solution, the most economic solution. So we're going to get straight into it. We've done this a bit with quadratics, and we used quadratic techniques in chapter 2 right at the end. That's a tough exercise. All right. Now this one's going to be tough as well, but we'll break it up into a series of steps, and we'll talk about what's the tricky parts, what's the easy parts of it. So it is a tough exercise, but I do have work solutions on the sector to guide you through it as well. So use those to help you along. All right, let's get into it. We've got the profit made by manufacturing X refrigerators per day is given by this equation. So we have, if we make one refrigerator, then we put X in there, we put the number 1 where the X is, that's going to be the profit made from making one refrigerator. We put X is 2 in there, that's going to be the profit from making 2 refrigerators. Now you might just go, oh, just make as many refrigerators as you can, because that's going to maximize your profit, right? But it's not necessarily the case. Let's say you've got this factory that produces refrigerators. Well, you need to maintain the equipment. If you don't do that, the equipment's going to deteriorate and it's going to have negative consequences moving forward. So there is some optimal amount of refrigerators to manufacture, right? And so that's what we're going to figure out. So here's our process, all right? The first step is to find the function. And if you're not given an equation, if you're not given the function, this is going to be the hardest part, okay? Finding the function, finding the equation. Here we're given it, so step 1 is done, all right? Excellent, we've got an equation. Step 2, differentiate the equation. Find P dash, all right? So if this is P of X, the profit function, we're gonna differentiate, we're gonna find P dash of X. All right, so minus 3 times 2x plus 240, and 800 just goes to 0. And you can do it in one step, right? You can have this. Okay, you can go straight to there, the minus 6x. Okay, so step 2, done. Step 3, draw the sign diagram of the derivative function. So we want to draw the sign diagram of this. We can go straight to our calculator and graph it. Okay, you can graph this and then graph the derivative from your calculator. Again, use your calculator to support you. So if we want to draw the sign diagram, like let's make the mathematical argument first. If we want to draw the sign diagram, we need to know when does it equal 0. That's when, minus 6x is minus 240. So x is minus 240 on minus 6, which is 40. All right, we've got the x value is 40. That's the root. So here's 40. And this is the equation of a line, but this time it has negative slope, which means it's going down. It has negative slope. So that means it's coming from above the x-axis to below the x-axis. All right. So we've drawn the sign diagram of P dash of x. All right. So what have we done? Here's the function. We differentiated it. We draw the sign diagram. You can get that straight from your calculator, right? Now, what does this tell us about the original function? Remember, we're backtracking here. P dash of x is the slope function. It tells you you have positive slope until you get to 40, and then you have negative slope. So if you have positive slope and then negative slope, what's going on there? You have a local maximum on the original function. So that means the maximum profit occurs when we make 40 refrigerators, okay? The maximum profit occurs when we make 40 refrigerators. So how many refrigerators should be made to maximize profits? So we've done part 1, 2, 3, we're up to 4, the optimal solution. 40 refrigerators. What is the maximum profit? Well, this is the profit function. This tells you the profit for any number of refrigerators manufactured. So we need to find P of 40. All right, we want to know what is the profit value when we put X is 40 in. And so we'll have minus 3 times 40 squared plus 240 times 40. Take 800. We'll mash that quickly. So what have we got? Minus 3 times 40 squared plus 240 times 40, and then take 800. I've got $4,000 is the maximum profit. Okay, so again, what have we done? Differentiate, draw the sign diagram. That's going to tell you the value of the optimal solution, and then solve whatever it's asking you for. Sometimes it's dimensions, sometimes it's something different. Okay, question 2. All right, so we've got here a box. And we've got X, these are equal, the base is equal, and we've got Y. Okay, a 2-litre box, and these lengths here are centimetres. Explain why Y equals 2,000 on X squared. So this is one where we have to develop the equation ourselves. Well, if we look at the volume of this box, okay, the volume of a 3-dimensional prism is the base times the width times the height, right? So the volume of this is X times Y, which is X squared Y. And the volume is 2 litres, which is the same as 2,000 centimetres cubed. 2 litres is 2,000 centimetres cubed, or 2,000 millilitres. And so if we rearrange this, we'll get Y is 2,000 on top of X squared. So that kind of thing, that's hard, right? That's not something we expect you to be able to do just by looking at it. That's something you need to be taught, you need exposure to, you need to develop a bit of confidence with. But that's how we arrive at the proof of part A. Part B, show that the area of the box is given by this equation. Where that's the surface area of the box. So this is what we're doing here. Again, we're still on part 1. We're finding the function. Now, most of the time in the textbook, they give it to you. In a test circumstance, we will always give you the function so that even if you can't find it, you can still go on to differentiate it and get the marks for these parts. Okay? In the textbook, they don't always do it, but in the test situation, we always will. Okay, so we are asked, show that the surface area, all right, the area of all of the surfaces added together. So what we have, right, is we've got 4 walls. We've got one wall here, one at the back and one on the other side. So we've got 4 walls. And we're told as well, it's an open top box, which means there's no lid, but there is a base. So we have 4 walls plus the base. Now, each wall has an area of X times by Y, okay? If this length is Y, the area of each wall is X times Y. So our surface area then is 4XY for the walls. And the base is X times X. So X squared for the base. But the problem with this function is we have 2 variables. We have X and Y. And that's why we did this first part, all right, is we've isolated, we've got a substitution for the variable Y. We're going to take this 2,000 on X squared and put it where the Y is. And we're going to reduce it from 2 variables to 1. So it becomes 4X times 2,000 on X squared, all right, putting that, Y is that. So we're putting that where the Y is, and then we have plus X squared here. All right, and we'll simplify that. That's going to be 8,000X on top of X squared. All right, now you can use index laws to simplify this part here. Another way is to think about it in terms of algebraic notation. So we've got 8,000x there, and at the bottom we've got x times x. Now one thing we've said repeatedly is if you have the same thing that multiplies at the top as you do at the bottom, it can cancel. So we can cancel x there, we can cancel it there. And so it simplifies to 8,000 on x plus x squared. All right, which is, I mean, we've just got it written around a different way, but we've arrived at the function that they're looking for. That's the surface area of all of the surfaces of this box with regards to x. Okay, so you can see part one, that's quite challenging, find the function. All right, on to step two, we're going to differentiate this function. All right, so we're up to part two, differentiate the function. They're saying part C, find the dimensions which minimize. All right, so that's the optimal solution. So we've got the function is, I'm going to write it like this, 8,000 x to the minus 1 plus x squared. And the reason I write it like that is because now we can differentiate it. All right, when it's written like this, it's a fraction. Remember we've said if you want to differentiate it, move it to the top, make the power negative, and now it's ready to differentiate. So that's the a of x function, the area with regards to x. Let's find a dash of x. So the minus 1 comes out the front. It's going to be minus 8,000 x to the minus 1 take 1. And then plus 2x. Okay, so we've differentiated. So that's step 2 done. Now we need to draw the sign diagram. Again, you can just graph this and get it straight from your graph. But let's make the mathematical argument, okay? The sign diagram is going to, the root is going to occur when it's equal to 0. And if we simplify this, what it is we've got minus 8,000 on top of x squared plus 2x equals 0. All right, so all I've done is move the x to the minus 2 to the bottom. So we're trying to solve this equation. There's a number of ways we can go about it. What we definitely need to do is get rid of this denominator, okay? We can't have a variable at the bottom. So the first thing we'll do is multiply both sides by x squared. So I'm going to multiply here by x squared and here by x squared. All right. And so what that does is that gives me x squared at the top, x squared at the bottom. It's going to cancel on this component, right? And then we have x squared times the 2x. That will be 2x to the power of 3. So we have minus 8,000 plus 2x to the 3 is 0. Now we've got the x to the 3 part by itself. We're trying to solve for x. So let's shove the number over the other side. We'll have 2x to the power of 3 is 8,000. Divide both sides by 2. We'll have x to the power of 3 is the cubed root of 8,000. Sorry, x to the power of, excuse me, messed that up a bit. X to the power of 3 is 4,000. Divide both sides by 2. And then we'll cube root both sides. Cube root of 4,000. Put that in our calculator. Do it quickly in my head. Cube root. $15.87. Okay, so we've gone through, all we've done there is got the x value that's providing the root for our sign diagram. It's 15.87 and it's a minimum because we're minimizing the surface area. So what that means, I'm thinking about it, I'm going, it's a minimum. That means it goes from decreasing to increasing, right? So it's negative to positive. That's going to be a minimum point. So you can think about these things in retrospect, in hindsight. So we've got the sign diagram there. That tells us the local minimum at 15.87. You can get that straight from here, right? Graph that, G-solve that point, draw the sign diagram. You've done that part. All right. So the question asks us, find the dimensions of the box which minimize its surface area. Well, the x value is 15.87. What's the y value? Well, the y value is 2000 divided by x squared. So that means it's minimized when y is 2000 divided by the x value, 15.87 squared. Put that into our calculator. And we've got 7.937. I'll round that to 7.94. Okay, so then the dimensions of the box. Well, the box is x times y. So that's 15.87 times 15.87 times 7.94. Okay, they're the dimensions which will provide the minimum surface area. And then part D, find the surface area. Well, we've found the dimensions. We want the minimum surface area. Well, this is the area function, right? Here it is here. I also stated it up there. And we want to know what is the area when the x value is 15.87. And so we just put it in 8,000 times 15.87 to the minus 1 plus 15.87 squared. So let's do that. We've got 8,000 divided by 15.87 plus 15.87 squared. 755.9, 756, and centimeters squared. The area is in terms of centimeters. I should put centimeters over here for our dimensions as well. We should always have units. Okay, so let's just have a quick chat about what we did there. All right, so in the second question, we spent most of it trying to get the equation. Once we have the equation, we differentiate it, draw its sign diagram. Okay, that gives us the optimal solution. And then we answer the question. It's often asking about dimensions. It's often asking about area and so forth. So guys, I better stop there. We do have question 3, but that I don't want to make it too complex already. I think we can go through that towards the end of the lesson. So we're 15F, optimization. And I think that's probably a good one for us to start with. So have a look at question 1, 2, 3. All right. Yep, let's go into that.